Okay, so the reason why I took this term is, well, if you look at these expressions over here, which I need to integrate over R, they are all the products of two exponents, one containing K1, the other one containing K2 of R, K2 times R with plus or minus signs. But now I know what the result will be when I integrate over R. K1 and K2, they might change signs. I might get K1 plus K2 over there in the Dirac delta. But other than that, all of them will be exactly the same. So now let's evaluate that term. Q will be equal to d cubed R, J0, which will be, well, I have I times all these terms. D cubed K1, D cubed K2, divided by 2 pi cubed from K1, 2 pi cubed from K2, and then I have 1 over twice omega K1, twice omega K2, raised to the power 1/2, the square root. And now let's keep writing. Well, all of them will have a 2 pi cubed after our integration. So I will write the 2 pi cubed out. I will take it out. I will only write the Dirac delta parts, and if there are any, I will write the exponents. Well, let's see. The product of these two. I have AK1, AK2 dagger. But then the remaining integral is minus IK1R plus IK2R. It is exactly this result. So I just have a Dirac delta. It's exactly equal to this integral. I have a Dirac delta K1 minus K2. Now, this term is what I obtained from the product of these first two terms in that square parentheses. Then I can take this product, the first term in the first parenthesis and the second term in the second parenthesis. So that will give me a minus AK1 BK1. So these are BK1. Minus AK1 BK2 with no dagger. And then I have both K in the exponents. Both of the exponents are negative. What will that change in this derivation will be, I will get a Dirac delta K1 plus K2 instead of K1 minus K2, but the exponents don't cancel because the exponents also change, have the same sign. Yeah, that's actually something that I wouldn't like to have, but see what will happen. Let's see what will happen to that. Now I have the second term multiplied by the first term. So that is BK1 dagger, AK2 dagger. Both are daggered. And then I have, again, the exponents. They are the same sign. In the previous case, they were both minus IK1R minus IK2R. This time is plus IK1R plus IK2R. Well, the result will be e to power I omega K1 plus omega K2 of T, the three-dimensional Dirac delta of K1 plus K2. And also let me not forget that I have an I omega K2 factor. Which I take out because you see both of these terms have, okay, I'm kind of jumping some steps, all the terms will have either Dirac delta k1 minus k2, which will make k1 equal to k2, which will make omega k1 equal to omega 2 k2, or I will have Dirac delta k1 plus k2, which will make those two momentums with opposite signs, but since omegas depend only on the square of the momenta, changing sign won't make any difference. So in all the terms, the Dirac deltas will make sure that omega k2 and omega k1 are the same. So that's why I just take out an omega k2, I omega k2 out, and I'm fine with it. Well, let's continue. Then I have the second term from both of those expressions. No, this is plus, by the way, because I'm taking the first term in the first parenthesis, the second term in the first parenthesis, and the first term in the second parenthesis. That's a plus sign. Now I have the second terms, the product of the second terms. I have minus bk1 dagger bk2, bk1 dagger bk2. Well, the exponents, one is a plus, the other one is a minus, so there's no exponents, and I just have a Dirac delta, three-dimensional Dirac delta of k1 plus k2. This is the R integral of this first line. Now let's look at the second line. Well, there is this minus sign, and this minus sign makes the plus. I already took out that I omega k1 out, so I'm just left with these terms. Well, if I just multiply the first terms, I will get
K1 plus K2 or K1 minus?
AK1, AK2 dagger, Dirac delta K1 minus K2. The product of the first term and the second term, this is AK1, AK2, AK1, BK2. Well, the exponents will be e to power minus I omega k1 plus omega k2 times t plus k2. Yeah, this is nice, you see. This term cancels this one. You see, I'm calculating the charge. I claim that charge is conserved. It shouldn't depend on time. So all the time dependencies should somehow cancel. Well, at least I see one of the cancellation. Well, let's look at the other terms. I have the product of the second term and the first term in the other parentheses. So this will be minus bk1 dagger, ak2 dagger, both exponents are positive, e to power I omega k1 plus omega k2, Dirac delta cubed k1 plus k2. Now again, this term and this term, they exactly cancel each other. And then the second term in both parentheses, it will be a minus sign. Minus bk1 dagger bk2. So this is my charge. Let's simplify it further. Now, K1 is either equal to K2 or minus K2. In fact, in the remaining terms, K1 is equal to K2 exactly. So omega K1 will be equal to omega K2 when I evaluate the K2 integral. So this omega K's will cancel this one. This 2 pi cubed will cancel one of these 2 pi cubes. And then I have a minus over here, another minus over here. Let's say that this is a minus 1. And I have d cubed k1 divided by 2 pi cubed. And what is left is, there is these factors, 1 over 2. And I have this term, AK1 dagger. And well, I have two of them, this one and this one. And then I have this term and this term, again they're equal. Dirac deltas are gone. Yeah, that's it. These two will cancel these ones. Okay, if I didn't make any mistakes in the position of these operators, etc., this is our conserved charge.
This itself looks like a field.
Hmm?
This itself looks like a field.
Well, it's not a field in the sense that it doesn't depend on position. I have already integrated over all the positions.
So can't that be a momentum space field then?
It doesn't depend on momentum. It's a number. It's a constant. It doesn't depend on momentum. It doesn't depend on position. In that sense, it's not a field.
Integrated it over the K1, which is a K1. What's that K1 supposed to say?
Momentum, but that means that it doesn't depend on K. Yes, I'm integrating over K. That means it doesn't depend on K anymore.
No, we did. The K1.
Yes.
At the end.
K2 is equal to K1.
So far, the only thing we know about these A's and B's is their commutation. So, do we need to know any further?
Not
to
really.
make sense of what Q really is?
No, in a moment. Let me write this as, I can use the commutation relation to change their positions. Plus some constant. Well, you see, before your question, if I don't assume K mu equals to constant, I always get some constants, additive constants to this conserved quantity. I'm not so happy that I obtained this constant here, but I mean, if it is here, it doesn't really matter. It's by definition conserved, it doesn't change. By definition, it doesn't change with time. So what remains is also conserved. So this is conserved. Okay, conventionally, I would rather have, let's say, Q bar minus Q depends on, you see, what does this tell me? Let's say that I have a system that has one energy package of the type A. Then the charge, if I just look at that one, whatever that charge is, the corresponding charge is -1. And let's say that I can also imagine another system. Well, let me write it explicitly. Let me define these systems. K is equal to let me consider this system. 0 is the vacuum. What is the Q acting on this one? Now let's see. I know what Q is. This is, well, let me stick with this one. Minus d cubed k1 divided by 2 pi cubed a k1 dagger a k1 minus b k1 dagger b k1 a k dagger 0 times this square root of 2 omega k is just a normalization. Well, bk and ak, they commute with each other. It's bk1 a dagger k acting on empty state will be equal to ak dagger bk1 acting on the empty state. Annihilation operator acting on an empty state will just give me 0. So this term gives me 0. Let's look at this one, a k1 dagger a k1 a dagger k. This will be equal to acting on vacuum. Well, if I want to calculate these things, the general trick which we'll use over and over again is move the annihilation operator to the right so that it acts on the vacuum. It gives you 0. So you get one less operator. How do you move them to that operator? Well, use the commutation relationships. I just wrote AK1 AK dagger equal to AK1 AK dagger minus AK dagger AK1 and plus AK dagger AK1. But AK acting on the vacuum would give me 0. So this term won't give me any contribution. I know what this term is. This will be 2 pi cubed times the 3-dimensional Dirac delta of K1 minus K. So Q acting on Ka would give me minus square root of 2 omega k d cubed K1 over 2 pi cubed a K1 dagger 2 pi cubed Dirac delta of K1 minus K acting on vacuum. Well, now I can evaluate the K1 integral. That Dirac delta basically tells me that I should replace K1 with K everywhere. But this is nothing but my state with a minus sign, minus Ka. So I defined this charge operator in terms of my fields. And it turns out that if I consider a state that contains only one Ka particle, A-type particle, this is how I created it. Well, it just gives me 1. Well, it's not a big surprise. Just look at this form of Q. AK dagger A is nothing but the number operator for particles having momenta K1. I'm summing over all K1. So this charge operator is actually minus the number of A particles plus the number of B particles. Yes, this is the number operator of A particles. This is the number operator for B particles. This is my charge operator. So you see, when we had these complex fields, we first said that, okay, I have complex fields, so I have these two different operators. For the real field, when I looked at the Fourier transform, I had a single type of Fourier transform, the phi p and phi p star. Those terms had to be the same for my field to be real. But then, for complex fields, I said, let's say that I said that, okay, I don't have to have the same operator. Let me look at the, okay, this is my definition of the field. For a real field, A and B operators had to be identical. But then we introduce these complex fields, and then if they are complex, then A and B fields need not be identical. We didn't know what they correspond to, but the only thing we knew was they had the same mass before. A and B, the fields created by A and B, they had to have the same mass, because for both of them, omega k squared is equal to m squared plus k squared. For both of them, this was satisfied. So for both fields, the mass were the same. Now we know one difference between those two fields, the A kinds of fields and B kinds of fields. You see, they have different quantum, different charges. With my definition, with this definition of charge, with this minus sign, which conventionally doesn't exist there, A type of fields have a charge -1 and B type fields have a charge +1. So their A type and B type fields are such fields that they have the same mass but opposite charges. Those are what we call antiparticles, to distinguish them. The B-type particles is the antiparticle of an A-type particle, and the A-type particle is the antiparticle of a B-type particle, because they have the same mass. In fact, they will have almost every property will be the same, except on their charge. Their charge is different. Yes, questions?
I'm gonna ask something, but as a motivation for the second semester course, maybe. We start with the classical system, but then at some point we use the computational relation, so we basically use some principles from quantum physics.
Mm-hmm.
But how do we know that this symmetry is preserved in the quantum field?
So can you repeat the question?
How do we know that this symmetry is preserved when we employ the computational relation?
When
Can
you
there
qu-
be a case in which the system has this classical symmetry, but when we quantize the system, the symmetry doesn't survive after the quantization?
Okay, now we can also give the answer. Yes. You know the answer, come on.
Okay. There are certain situations in which you cannot fully preserve the classical symmetry when you quantize the system, and these are called basically the anomalies. You have actually one of those in quantum electrodynamics, which is the gamma-5 symmetry.
That is not quantum electrodynamics.
Let's say direct fermion with a gauge field. That's
No. In quantum electrodynamics, you don't have that. What he's talking about is, okay, we start with a classical system. We look at the Lagrangian. We define a transformation in the Lagrangian itself, and we look whether the Lagrangian changes or not. Then, of course, there's also this quantization procedure. Well, certain symmetries, certain systems have this property that quantization procedure itself breaks this symmetry. It doesn't respect this symmetry. That is what is an anomaly. And in fact, we do have cases. Quantum electrodynamics doesn't have an anomaly.
But you have to choose whether to preserve the charge conservation or the gamma-5.
No,
charge.
in quantum electrodynamics, we don't have gamma-5. That's why it doesn't have a...
Massless, let's say, massless quantum electrodynamics.
No, not even in massless quantum
No,
electrodynamics.
in massless case, we have the gamma-5 symmetry.
You don't... still, depends on how you write the quantum electrodynamic theory. In weak interactions, in principle, they have this anomaly. For example, in the standard model, the weak interactions themselves might have that anomaly. And anyway, we will probably discuss it. Well, we will discuss it in next semester if we discuss standard model. But for those who know some particle physics, let's say there are the up and down quarks and electron, neutrino, and electron itself. If you just sum the charges of all these ones, all these particles, the anomaly is proportional to this total charge, which turns out to be 0. So even the weak interactions, because we have all these particles. It doesn't have this anomaly. In principle, though, it could have this anomaly, but it doesn't. But that is a case where the Lagrangian itself is symmetric, but the quantization procedure itself would break the symmetry. I mean, when we look at path integrals, just ask again. I will give another explanation of why it doesn't appear. How does it break?
I have another question. This so-called charge we find may or may not correspond to the charge in the electrical sense. The choice is ours, right? It depends on the symmetry constants we choose. Like as you showed us that there are phase symmetries. Like we turn phi to the phi exponential I alpha or something. If we choose that alpha to be something that contains electrical charge, then this charge Q may turn into the electrical charge, right?
Well, you see, to be able to talk about the electric charge, first we have to introduce electromagnetic interactions. Without electromagnetic interactions, this is just a charge. We don't know what it is. But when we will introduce the electric charge, electromagnetic interactions, this Q will turn out to be the electric charge with a possible overall minus sign. So it will be a minus. You see, if you look at the electric charge, what is the electric charge? The number of positive charges minus the number of negative charges. So here A has a negative charge, so number of A particles is the number of negative charges, B is the positive charges, so the number of positive charges minus the number of negative charges. So this will be the electric charge, but since this theory doesn't contain any electromagnetic interactions, there's no sense within this theory to talk about the electric charge yet.
We generally say charge for historical purposes, right? It's a conserved quantity as an operator, but we say charge because we know Maxwell theory way before, and it's charging there as a conserved, so we say charge to this one.
What do you mean by charge?
Yeah, what I mean by a charge is a conserved quantity that can act as an operator, that can be written as an operator equation. I think of it as a charge in the sense.
Well, we have the electric charge.
Yeah. It's a conserved
It's
quantity again.
This is not necessarily the electric
It's-
charge. It might be the electric charge, but the name is charge.
Charge.
Let me look at another theory, another example, more or less along these lines. Rather than having one complex field, let me have two of them. Furthermore, let me assume that my Lagrangian is given by this term. I mean, you can also add the potential term if you like. But the potential term, I will also assume that it is a function of, it's not a function of phi 1 and phi 2 separately, but rather it's a function of phi 1 squared plus phi 2 squared. Well, in fact, if you just look at it, it just looks like the case where we had the phi 1 and phi 2 were real fields. But this time, phi 1 and phi 2 are not real fields, but they are themselves complex fields.
Is the first derivative a d or a partial?
It's a partial. Well, this also has a symmetry. Let me take phi 1 and phi 2 fields as a doublet. If I multiply this with a unitary symmetry, unitary matrix, so you see my Lagrangian is this one. let me call this doublet capital phi. Since phi dagger phi would be phi 1 star phi 2 star phi 1 phi 2, also the same will hold for the derivative one. Well, since u is unitary, phi dagger phi will be transformed into phi dagger, u phi dagger. This is how it will change. This is phi. But since u is unitary, this is 1. So this is another symmetry of my problem. I will also assume that the determinant of u is equal to 1. So 2 by 2 matrices, 2 by 2 unitary matrices with determinant is equal to 1. This is actually what we call the SU2. And in general, you can write any u in terms of 3 parameters as e to power I, alpha I, sigma I. Sigma I are the Pauli matrices. Well, my fields, phi becomes e to power I, alpha I, sigma I, phi, or for small alpha I, this is actually 1 plus I, alpha I, sigma I acting on phi. So this is phi plus I, alpha I, sigma I, phi. So this is my delta phi, the change in my field phi. And this is a symmetry, so I can write the corresponding conserved charge. Let me put the bar here. I see the current we defined using Noether's theorem, this one. Since delta phi also contains the parameters of our transformation, well, if they are constants, if we take them out, they will still be conserved. So the current actually is what we obtain when we factor out those constants, just like we did over here. You see, I obtained J mu, which was proportional to this transformation parameters. What remains is conserved, since this is just a constant.
Hocam, actually for n complex fields, we have SU n symmetry. And the
If
previous problem
Sure.
had SU1.
Sure. That's U1. SU1, there's no group. It's U1.
I mean, that exponential has mod 1.
Not the determinant one. If you impose determinant is equal to 1, you just have 1, the unit identity operator. So you have U1, but
Oh, yeah.
SU2, SU3,
That's
SU4. You don't have SU1. Anyway, let's continue with this. So what will be our current? Our current. Well, the derivative of the Lagrangian with respect to del mu phi and the variation of phi. Well, Lagrangian is invariant, so this is our current. Well, what will this be? This will be del mu phi dagger I alpha I. Oh, sorry. Let me also add to this one phi dagger, the variation of phi dagger. Derivative with respect to del mu phi just gives me del mu phi dagger. I have I alpha I sigma I phi. Then plus phi dagger minus I sigma alpha I sigma I. Sigma i's are Hermitian. That's why I don't have the dagger over there. And then del mu phi. This is my current. Well, this will be alpha I del mu phi dagger phi minus phi dagger del mu phi. And there's sigma I here. Let me change this I to J. It's a dummy index, but I don't want that index to be confused with the complex number I. Yeah, it's more or less identical to what we had done before. The only thing you have to pay attention to is now this capital phi is a matrix, so you have to be careful about the ordering of these things. And well, you see, alpha j are three numbers, three arbitrary numbers. Whatever those alpha j's are, this is a conserved quantity. For example, I can choose them such that alpha 1 is non-zero, the other ones are 0. So there's only all of these ones for each j from 1 to 3 are conserved. I have 3 conservation laws, not 1. Yeah, basically, because although we said that, okay, this is an SU2 symmetry, in a sense you can think of SU3 symmetry as 3 different symmetries, corresponds to alpha I being non-zero, only one first component, second component, or third component. Each of them are symmetries. So there is a corresponding conserved charge for each one of those symmetries, and they are given by this expression over here. So we don't even need to have one symmetry for one conservation law for one symmetry, but we have, if the symmetry is larger, then you can have more than one conserved charges. For example, weak interactions are described by a theory that has this SU2 symmetry, which will be broken, which we won't discuss now.
May I ask a question? Again, a simple confusion. So when we say rotation, like all 3, and when we say S all 3, I tend to imagine it as if we are choosing some kind of an orientation. So that we can take integrals and everything.
Mm-hmm.
But for the case of U2 and SU2, I sometimes find hard to imagine what we say actually by just saying that the determinant is 1. And how can I understand that other than that, okay, I'm now using the matrices, that the matrices correspond somehow determined to 1, and then these are somehow some representation of, and it's that like Pauli matrices. But I cannot, even in my head, I cannot find a clear understanding of why we said that not U2 but SU2 in here. What will be changing corresponding to that? So it's
Okay.
like not changing in orientation.
Well,
not
basically, I
exact-
heard 2 questions there. One is about choosing origin, and what's the difference between U2 and SU2?
Yeah, in that sense, how we will have.
So let's start with, what do you mean by choosing origin?
choosing orientation, I would say, but it's again.
You mean origin or orientation?
Orientation.
Yeah, orientation.
Orientation.
So what does rotational symmetry tell me about orientation?
So how I see it is like we are choosing that we are choosing our space's handedness so that when
Yeah, handedness is something else,
Ah,
something different than orientation.
okay.
I mean, if you mean handedness, okay, that's a different problem. But when you say orientation, I would just say how you orient your coordinate axis. And in fact, rotational symmetry tells me that nothing changes if you change your orientation. Your orientation, the orientation of your axis is not something physical. It shouldn't affect the physics. It's kind of arbitrary.
I believe
As
what he's trying to say is that when you take the S, you basically disregard the determinant minus one
yeah,
solution.
as we say plus or
Okay.
minus one, but we choose plus.
That's the
less.
very first thing.
Yes. Yeah.
Okay, so rotations tells me that your orientation is not physical. If you have a rotational symmetry, whether in real space or in this abstract complex space of the phi 1 and phi 2 complex fields. It just tells me that orientation is not important. Now, let's look at these two cases. So what do we mean by UN or SUN? Let's forget about field theory for the time being. Let's say that we have numbers that I from 1 to n. And we take their absolute squares and sum them up. Let us call this d squared. Because if you were in real space, we are basically if you look at the rotations, that's in real space. So you have three numbers in three-dimensional space. Let's say you have three numbers, you take their square and sum them up. And then you look at all the transformations of those three numbers that do not change that sum. So, for example, what do we mean by rotations? Well, there are the x, y, z coordinates of vectors. You just take their square, sum them up. That is the length of your vector. And SO3 is all the transformations of these three numbers, x, y, and z. That leaves this invariant, plus there is the determinant of O should be equal to 1.
Doesn't that all that stands for orthogonal?
Yeah.
What does orthogonality do with the equation of a sphere?
O transpose O is equal to 1 for these matrices. What basically this means is if you imagine these matrices as rows or columns, if you take any two rows as your vectors, they are orthogonal to each other. Or any two rows, they are orthogonal to each other. Well, probably that's why it's called orthogonal group.
Okay, logical.
Plus, if you imagine rotations, I mean, you can have very small rotations and large rotations. Any rotation, you create the rotation slowly. So let's say that you have this object. If I want to rotate it to this orientation, I rotate it continuously, right? So if you somehow want to describe this rotation by some parameters, and zero rotation, when those parameters are zero, you want to have the identity. So you want, but let's look at this transformation. 1, 1, minus 1. This transformation also leaves x squared plus y squared plus z squared invariant. It doesn't change it. But there's no way that I can find a transformation such that at some parameters of this transformation, I get this matrix, and when those parameters are set to 0, I get the identity matrix. It's not possible to find such a change. Or in a sense, I cannot change this matrix continuously and connect it to the identity. You see, this tells me that determinant O squared is 1, but that O is a matrix of real values, so determinant O is a real number. This tells me that determinant O is a plus or minus 1. So if I say that all transformations that leave, this combination invariant, well, some of them will have determinant 1, some of them will have determinant minus 1, independent of my parameters. So whatever parameters you choose, if you are changing parameters continuously, so the determinant should change continuously. You cannot have a continuous change from +1 to -1. That is always a discontinuous change. So if you consider all the transformations that leave this combination invariant, they are basically split into two. Those that have determinant equal to 1, and by changing their parameters, I can always connect it to identity, and those that have determinant -1. And those, I cannot change their parameters such that eventually I recover the identity. So it's said that there's a O3. All transformations that change x squared plus y squared plus z squared is actually O3. O3, I can divide it into two. One, transformations that leave transformations that have determinant 1, the other one, transformations that have determinant -1. Well, if you have a, let's say, O1 element of O3, O2, which is an element of O3, but not an element of SO3, let me call this matrix P. PO2 will be an element of SO3. So, I mean, we actually divide it into two sets of equal size, if you like. I have this one connected to identity, this one disconnected from identity, but for each element over here, I can find another one over here. Hold on. And I forgot what I was about to say. Anyway, yes.
Jim, I think I figured out the answer to his question. So, in all of our arguments, we actually use only unitariness and not special unitariness, right?
No.
Well, yeah, special unitary feature comes in when we exponentiate and.
Yes.
So we want to work with a Lie group rather than.
We are looking at infinitesimal changes.
Right.
Now, I remembered what I was saying.
Because
you
we want to use symmetries and stuff.
You see, SO3 itself is a group.
Yes.
O2, those are elements of O3 that are not elements of SO3. They are not a group, because if you multiply any element of O3, which is not in this special group, their determinant will still be 1. Both of these are -1, the product is 1. So the product doesn't have the same determinant. But if you look at any elements over here, their determinant is 1, their product will have the same determinant. So these form a group, these do not form a group. Well, in physics, we always tend to look at very small changes, so we would like to be close to the identity. Now, where did I assume, by the way, the special group rather than the unitary group? Right over here. If I didn't add an plus I delta, let's say, proportional to identity. But UN, is this always true? I think so.
always an
Yeah.
operator. So.
Anyway, the next day they will be kicking us out.
Can we interpret the SU like SO leaves the norm of the vector invariant? And physically, what SUN stands for is that it leaves probability invariance.
No.
Can we,
Yeah, you see,
What's always you, right?
you see, real space
Yes.
is a real valued space in the sense that I have vectors whose components are real numbers. I can also imagine spaces where the components are complex numbers. There I can also define a norm. In that case, the norm will be just the absolute value of the component squared summed over this one. So in a sense, UN is just like rotations, but not in a vector space not in a real vector space, but in a complex vector space. I would rather avoid the probability interpretation, because that is for a in quantum mechanics it will be probability. In other places, I mean, this thing is not a probability. Anyway, they have an exam, so I mean, we can continue outside.